Okay, so let's start. First thing first, is AI going to take our job? Is self-attention, transformers going to leave us without any day job? The answer is probably no. So I went online, I got some other news from 87. I wasn't even born in 87, when people thought that programming is a dead end. Okay, why? Because of programs like LabVIEW. I don't know how many of you know what LabVIEW is, but once programming became somewhat visual, people thought this is the end. People gonna program without any prior knowledge. Programming is a dead-end job, so probably not. When Python became popular, people thought, hey, this is becoming too easy. Programming is not even a challenge anymore. People can create programs without experience, whatever. This was roughly 20 years ago. They thought programming is at an end. And most likely in intervals of 20 years, we reached this same point again. Is GPT going to make us all unemployed? Well, probably not. I have several standing bets with people I will not name about this. If you're interested, come after the lecture. I'll bet with you as well. So a bit about myself. My name is Alon. I'm the VP Research at Dynamic Infrastructure, a startup company working on solving transportation infrastructure using AI, LLMs, object detection, etc. And I'm also the lead project advisor at the MLDS, Machine Learning Data Science MSc program at Reichman University, where I also teach several courses. Okay, so enough about me. Let's get down to business. So the reason I created this talk is I started getting into deep learning roughly at 2015. I got a job, let's say 4 years afterwards. I was a student, so 4 years afterwards. And then I skipped attention. So I had nobody teaching me self-attention. And then transformers became obviously extremely popular. I started using transformers at my research and at my day job. But I didn't understand the mechanism behind self-attention. I tried reading the original paper, Attention is All You Need. It's a terrible paper to read. It's not very coherent. So I got into, so those are the animations from the paper. They are quite intimidating, not very informative. It's not clear why they chose, obviously, those three dreadful letters, QKV. So I got into it, and I created this presentation to let you all know how self-attention actually works. Okay, so let's start with something simple. And obviously, self-attention is the base for the transformer architecture, which is the T in GPT. So obviously, all of us are using QKV several times a day. So let's start with the basics. Okay, and the basics is the perceptron, basically a simple linear layer. Obviously, people in deep learning like to invent complicated names for pretty straightforward stuff, like the perceptron instead of a linear layer, or back propagation instead of a derivative. But this is the basic idea. Okay, we have the inputs, we have weights, we multiply them together, we sum them up, we might activate it, or again, another name, a fancy name for just introducing a nonlinearity, and calculate our input. Okay, so this is the basic scheme of a neural network. So we can create we have several ways to make this more complex. We can add more neurons per layer, more perceptrons per layer. We can increase the amount of layers. So this is obviously a very simple snippet from PyTorch. This is completely abstract. We don't have to worry about the weights. We won't have to worry about the connections themselves. The basic premise is that we have a sequential architecture where every input is derived into the output, and every output is the input to the subsequent layers. Okay, so this is encapsulated with this very simple code snippet. So again, we can create, instead of a 2-layer network, we can create a 3-layer network, and it's basically a very nice Lego that we can play around with. Okay, so we can use this very simple Lego architecture and solve classification problems where we have a single input and a single output, We can perform sentiment analysis. If we're analyzing, for example, sentences, we have multiple, obviously, inputs, multiple words or multiple characters, but we have still a single output, or we can do something a bit different, which is image captioning, which is a single input, an image, where we want to create an entire sentence. Obviously, I have more than a single output. So let's shrink down this representation of neural networks, okay, into this, and let's handle time series. Okay, so this is a time series. I have characters. If I want to maybe perform name classification, so I have the characters of the name, Alon, A-L-O-N, and I want to carry memory from one neural cell or from one neuron to the other. So most of us know this architecture by the name RNN, okay, recurrent neural network. So what this RNN is doing is evolving, right, the representation of whatever is going on, starting from the A. We carry some information using the hidden states. So once the network comes across the next character in my name, L, it remembers, it knows something about the previous character, and so on and so forth. So once we read the entire sentence, we can obviously tell something about the entire thing because we have already exhausted all the text we wanted to read. Okay? So this is a very quick overview of what RNN is. So RNN is a very nice and elegant way to handle sequential data. Right? We have multiple states, we have the memory. Sounds sort of like how people deal with sequential data. It can support very naturally varying lengths. Everything works. There are several issues. It's hard to train, and the performance is quite limited in certain tasks. Okay? So let's dive into self-attention, because we already have everything we need in order to introduce self-attention. So let's start with something, just one last thing, word embeddings. So we won't introduce the input to the self-attention mechanism with single characters one at a time. We will do it with entire words. Why? That's an entire different lecture, why word embeddings are better than characters. But if we have those word embeddings, and those word embeddings were trained properly, they carry some semantic and syntactic information about the language. And we want to use that information so the self-attention mechanism won't have to learn it by itself. That's word embeddings 101. Okay? So for example, most of you are familiar with those analogies, right? Teacher is to school as doctor is to hospital. So this is the information the embedding carries. Okay? So we will use embeddings instead of characters. So here is a sentence. The colorful hot air balloons floated above the valley. Okay? Those are the embeddings, all the brownish, purplish rectangles that we can see. Okay? And those images are what you would expect to get if you would take this embedding and put it to something like Midjourney. Okay? So once we start, okay, the embeddings, the original embeddings that we get carry some very general information about the word that they represent. For example, colorful, obviously many colors, hot, fire, air, clouds, and balloons, just ordinary balloons. But if I have a sentence like the colorful hot air balloons, obviously I want to evolve the representation of the embedding, right? I want to improve the embedding of the word balloons, because it's no longer generic balloons. Those are hot air balloons, which are obviously entirely different. Okay, so this is the goal of attention. This is what attention is trying to achieve. It's trying to create a better, more nuanced representation of each word. Okay, so now, if you can imagine, I'm taking a sort of a weighted average. I'm averaging those embeddings in a certain way, and if everything works, okay, if I believe that backpropagation and optimization and everything works, instead of having those embeddings at the very start, maintaining their structure along the depth of the neural network, I want to have a better representation. So self-attention, we do this process for every single embedding. Okay? So how can I create this embedding? And this is just a single one. So as I'm evolving the representation of the word balloon, I will also evolve the representation of the word air, hot, colorful, floated above the valley, etc., etc., etc. Okay, I will do it simultaneously. So how would we create this new embedding? Okay, so we will score every input embedding against all others. We would measure how similar they are. How can we do this operation in neural networks? Maybe a dot product, something very simple. I'll show some code in a second. Okay? And then we will take the weighted sum. So obviously, instead of just a simple weighted sum and a simple dot product, we will introduce some neural networks in the process to make it more complex. But that's the basic idea. Okay? So if you're having trouble remembering what's happening in self-attention, it's basically a dot product and then a weighted average. Okay. So let's see what happens. We would take this dot product, okay, and we would score every embedding against all others. For now, we would just focus on E5, okay, balloons. Okay, we will take the weighted sum. Okay, we'll take the weighted sum, and the updated balloon embedding, it's basically nothing more than a linear combination of the attention scores, the C's, the dot products, with the original embeddings. Okay? So I'm doing two things. I'm using the embeddings in order to create the distance, and I'm using again the embeddings to calculate the weighted average. Okay? I'm double dipping, and we'll solve it in a second. Before solving it, let's see what's going on. So you saw previously that I only had a single layer of self-attention. I can obviously have multiple layers of self-attention in the same way that I'm stacking linear layers in a normal deep learning architecture. Okay, so as I progress, as I introduce more and more and more self-attention layers in my architecture, I can get a better and more nuanced representation of each embedding. Okay, so as you can see, for example, the embedding obviously for balloons is evolving into something that is more a colorful hot air balloon. The embedding for floated obviously captures the valley that we talked about previously and the hot air balloons obviously in the scene. So if everything works, as I'll use self-attention again and again and again, my embeddings would be better and better. And what should I do at the very end with those very fine-tuned and contextualized embeddings? I will just use a simple linear layer and calculate whatever I'm trying to calculate and optimize it using backpropagation. Okay? So let's see how it's actually calculated. So you remember the double dipping from the previous slide? So let's solve this double dipping. Why? Because this would hopefully be, or it would have more computational power. More neurons, more computational power, we're kind of used to it. So let's see how to disentangle the issue that we had previously. So instead of having just the embedding X, we would create three embeddings, Q, K, and V. Q and K would have the role of calculating the distance. But why do I need two vectors to calculate distance? Because I want this distance to be asymmetrical. If I'm calculating the distance from myself to you, or from you to me, I want this distance to be not necessarily the same. Okay? So instead of, for example, when hot is being calculated versus balloons, or balloons are being calculated versus hot, I want this distance to not necessarily be the same. So if balloon is querying the word, if balloon is asking the word, the embedding hot, what are the distances? One would, and don't remember, I don't remember which one, okay? Doesn't really matter for the intuition. In one case, when balloon is asking if balloon is asking, it will present Q. And if balloon is being asked by someone else, it would present K. Okay, that's it. So Q and K are the way we handle this asymmetrical distance function. What do we need V for? I don't necessarily want to perform the weighted average on the original X. Maybe it's restricting me in some way. So I would give the vector that I'm going to use for the weighted average a chance to maybe evolve or to be better represented for this weighted average operation. So this is the goal of V. Okay, so this is QKV. And some people say that the name transformer comes from this slide because we're transforming the vector X into 3 distinct vectors. Okay, Q, K, and V. And now let's understand it with some code. Okay, so I have 3 matrices that are gonna perform a projection on the original X and transform it to Q, K, and V. For simplicity, I can just concatenate them, right, to a single large matrix. Okay, a single large matrix, W underscore QKV. From there, I can add the bias, okay, obviously. I perform this dot product, and then I'll just split it, okay, into 3 distinct vectors, Q, K, and V. Pretty straightforward. Now for the self-attention part. So a bit scarier, okay, but still pretty straightforward. So the entire self-attention mechanism is written in a single line, okay? So Q dot K, okay, forget about the transposers for a second. This is calculating the distance, right? That's the dot product in matrix form. I'm dividing it by the square root of the dimension. Don't worry, you're probably used to terms like this. I'm sort of normalizing it. And then I'm just calculating again another dot product with V. Okay? So I'm calculating the distance, performing a weighted average. This is it. This is self-attention. Okay? And if it would help, this is the gist. Okay? It won't work. Don't try to implement it. Don't say Alon doesn't know anything about self-attention. But it's the main logic. Okay? I'm taking the original embedding X, I'm splitting it to QKV, I'm calculating the updated representation using the scoring mechanism and the weighted average, and I have a fully connected network, fully connected layer that you're familiar with that we will discuss in a second. Okay, so why do we need self-attention, or why self-attention is so effective? Okay, so let's get back to fully connected networks. Okay? So I have inputs. I'm plugging them into some fully connected network. Okay? I have the fully connected weights. This network is already trained. The fully connected weights are static. They won't change. So if I'm changing, okay, if I'm changing a single input, if I'm changing this input, the 5th one, okay, this architecture, the fully connected architecture, limits how the input is going to change, right, based on the weight of that specific neuron. Right? It can't change more than 5%, the actual output, because the weight is static. This input has an assigned weight of 5%. So changing this would affect the outcome by that much. In self-attention, we have another mechanism. In self-attention, once we score every embedding against every other embedding, once we change a single input, what might happen? All weights would change. Okay? All weights might change. So this is a much stronger architecture, or even a generalization of the fully connected network, because it can react in a stronger, more violent way to small changes in the input, which is obviously something we want. Because if we're analyzing a sentence and you only change one single word, obviously the semantic nature of that sentence can vary in a very large manner. Okay? So this architecture, or this layer, is the base for a new architecture that is called the transformer. So everything we need is already in place to understand the transformer. So instead of having just plain self-attentions, one on top of the other, we'll introduce something slightly more complex. Okay? It's called the decoder block. Why block? Because it has several components. So we have the self-attention layer that we're already familiar with. We have add and normalize, pretty straightforward. We have a fully connected layer, obviously pretty straightforward, and then another add and normalize. So basically some normalization, some residual connections, as you can see, with the dotted lines, some fully connected networks for good measure, and obviously the self-attention at the very start. So this is a transformer block. Residual connections, normalizations, and attention. So now we can use this architecture. Instead of using one transformer block, let's use 6 of them. Okay? And now we can generate language in the same way that GPT is generating language. So we will introduce, again, the same sentence, the colorful. We will plug it into whatever architecture that we have. We'll have many embeddings at the very end. We would project it again and perform a softmax in order to choose the most probable word. But the main architecture is, again, all those decoder blocks that are stacked one on top of each other. Okay, so this is the main idea behind GPT. Okay, so this is the architecture of GPT. So it's basically, instead of 6, it's 12 decoder blocks stacked on top of each other. Instead of just plugging in the input, we have something that is called positional embedding. Don't worry about it. It's not very interesting. But this is GPT-1. Okay? So I'm training GPT-1 with a load of text. I have another step, okay, that now sounds maybe trivial, that is to tune it on specific tasks. And how should I tune GPT on specific tasks? I'll introduce something that now, again, is trivial, that is called a prompt. So I'll tell this architecture when am I starting, when is the sentence starts, when does it end, and the delimiter if I'm doing a multiple choice, again, a delimiter if I'm trying to do similarity, if I'm trying to perform classification. So I'll have a prompt and a different prompt for each task. Okay, and that was the good old days of GPT-1. Once we started increasing the amount of parameters, increasing the amounts of data, this phase was completely forgotten. And it was trained again in an unsupervised way, no fine-tuning. By that time, they had much more data, but by that time, they started sharing less and less and less information about what they were actually doing. But if you want, again, if you want to plug in the information that we had previously about self-attention, fully connected, and transformer block to a GPT, so this is basically how a very mini GPT actually works. So we have those stacked transformer blocks. We just iterate. We're reintroducing the input again and again and again. And once we have our fine-tuned representation, now we can do a softmax or whatever we want. So in GPT-3, okay, they basically did more of the same. They just used a lot more parameters, a lot more data. The batch size has increased tremendously, and what they got was a slide or a graph that you probably saw at least once. We saw a huge improvement in the performance, okay, even on one shot and zero shot and few shot performance on a very wide range of tasks. So this is when people started getting worried about the potential or harmful potential of GPT and language modeling. But so the missing part here, because if you try to use GPT-3, it wasn't very good. So they had an additional step that now we are calling alignment. or reinforcement learning human feedback. Okay, so this model has many capabilities. It understands, obviously, language excellently, and even GPT-4 is probably just, again, decoder blocks stacked on top of each other with better data, more parameters, and much more alignment than previous models. So some final notes, because my time is up. Self-attention is nothing more than an asymmetric and dynamic weighting function. Okay, that's it. And it's a generalization of the fully connected layer. Okay, it's just a fully connected layer that can adjust the weights as it sees new inputs. The transformer is a new architecture that is built solely on the self-attention idea. And they can model long dependencies that basically solve most of the problems that people try to solve once RNNs came out. And the next step that OpenAI and other companies are still tackling is to align those language models with human values and human preferences. Thank you.